Hi everyone and welcome to the next lecture in machine learning for core engineering disciplines. In the last lecture we started discussing about model training and we presented the example of the gradient descent or the steepest descent algorithm as the simplest algorithm of first order which can be used to converge the set of parameters to a local minimum for the loss function, and we discussed why if the Hessian matrix is positive definite, right, then that means that we have reached a local minimum, right. We also saw that the gradient should be low at the point of a local minimum, but one point we did not discuss last time was the link between the positivity of the eigenvalues of the Hessian and the positive definite nature of the Hessian matrix. So let's go ahead and clarify that. So the topic for today is training of ML models, and we are particularly looking at the gradient descent algorithm. Right, and by now you already know that the equation for the gradient descent algorithm is that the beta, which is the set of parameters at iteration k plus 1, is beta the set of parameters at iteration k minus gamma times the gradient, right, of the loss function at beta k, right. So this is the equation for the gradient descent algorithm. This gamma is known as the learning rate and beta is the vector of model parameters at iteration k plus 1. Okay, so this is how it works, and then we had shown, right, the sort of derivation of the gradient descent algorithm using the Taylor series, right. So using the Taylor series for the loss function, so you had L at beta plus delta beta was equal to L of beta plus the transpose of the gradient times the delta beta vector. This is basically trying to emulate a dot product, and then you had half delta beta transpose the Hessian times delta beta, right. And we said that at a minimum this term is 0, right, gradient is close to 0 at a minimum. And then we said that if this Hessian is positive definite, right, if H is positive definite, that means this term will always be greater than or equal to 0, which means that the value of the loss function at beta plus delta beta would be higher than the value of the loss function at beta, which is what is required at a minimum, right. So therefore a positive definite Hessian ensures a local minimum. Okay, so this is what was going on, and let's now see the link between the positive eigenvalues of H and its positive definite nature, right. So what do eigenvalues have to do with this? So the question we want to answer is, why do the eigenvalues of H determine the sign of Z transpose H Z, right, and in this case H is basically the vector delta beta. Okay. So now to answer this question, right, it is important to recognize that any real symmetric matrix. So we are going to work with real parameters here and real functions. H can be diagonalized as follows. So you are able to write H as the product of three matrices Q lambda Q transpose, okay, and this is uppercase lambda. Here these matrices are certain special types of matrices. So Q is an orthogonal matrix formed by the eigenvectors of H, right, and because Q is orthogonal, what this means is that the transpose of Q is the inverse of Q, which means Q times Q transpose is equal to Q transpose Q, and both are equal to the identity matrix. Right. So this is the meaning of an orthogonal matrix. The other thing that's special about this equation, right, is that this lambda is a diagonal matrix formed by the eigenvalues. Okay. So essentially this lambda is the matrix of lambda 1 lambda 2, right, up to lambda p here, and then all zeros otherwise, right. So I hope this makes sense. So that is why this lambda, uppercase lambda, is a diagonal matrix. Now what you can see is that we want to determine the sign of Z transpose Hz, right, because this was the term that appeared in the Taylor series expansion of the loss function. So how do we do that, right? Let us consider this quantity Z transpose Hz. So Z transpose Hz, and I am going to omit the arrow above Z, is basically equal to Z transpose using this transformation, right, eigenvalue decomposition, you get Q lambda Q transpose times Z here, right, and this can be written in a slightly different way. So this is Z transpose Q times lambda times Q transpose Z. So this is Q transpose Z whole transpose times lambda times Q transpose Z, right. I hope you can see that Z transpose Q is same as Q transpose Z whole transpose. That is because if you have two matrices, then A B transpose is B transpose A transpose, right. This you must remember from your earlier studies of matrices. Okay. So now if you let Q transpose Z as some W, right, since Q is an orthogonal matrix, basically the norm of Z and the norm of W will be the same, right. So now Z transpose H Z will basically be equal to W transpose lambda W, right, because this is W transpose, this is lambda, and this is W. So, Z transpose H Z is equal to W transpose lambda W. That is what we have written here. Now, let us see how this looks, right. So, W transpose is basically some sort of a matrix like this, sorry, vector like this, and then you have a diagonal matrix lambda 1, lambda 2 up to lambda n with zeros elsewhere, and then you have again W 1, W 2 all the way up to W n. Okay, or if you want to be precise, then this is W p because your Hessian is of size p by p. Okay, so if you look at this, this is really nice because this is a diagonal matrix, the lambda matrix, your W will just get multiplied with lambda 1, which in turn will get multiplied again with W 1. So, if you were to write this out, this would simply be lambda 1 W 1 squared plus lambda 2 W 2 squared all the way up to lambda p W p squared, and this can be written as sum I going from 1 to p lambda I W I squared. Okay. So, now if lambda I, which are the eigenvalues of H, are all positive, then clearly your Z transpose H Z, which is equal to sum I going from 1 to p lambda I W I square, will be greater than 0, right, and it will be less than 0 if lambda I are all negative. So, this is why, right, we can write the following statement. So, if the eigenvalues of the Hessian are all positive, then that would mean that the Hessian is positive definite. So, for any vector z, z transpose H z will be strictly greater than 0, and this would mean that we have a local minimum of the loss function. So, I hope you are able to see, right, why it is so important for the eigenvalues of the Hessian to be all positive, right, to lead to a local minimum of the loss function. Okay. And instead, if the lambda I were all negative, what you would have is basically it will be a local maximum, right, because Z transpose H Z would be less than 0. So, in any direction you move, you are going to encounter a lower value, right, of the function, and therefore, you will be at a local maximum. Okay. So, now let us rewind a few lectures, right, and recall what we had done in linear regression, right. So, if you recalled in linear regression, right, we had beta hat, the optimal set of parameters was x transpose x inverse x transpose y. Okay. And if you also remember the Taylor series expansion, the second order derivative, right, the derivative of the loss function, right, with respect to beta, that involved involve the matrix x transpose x, right, and at that point I had remarked that x transpose x, right, is mostly positive definite, and therefore, right, it is the optimal set of parameters correspond to a local minimum, right. So, this was for the case of linear regression, where x was the matrix of data points and their features, and y was a vector of true values. So, there we had sort of left the problem saying that look, x transpose x is most likely positive definite. So, it is indeed a local minimum of the loss function, and we had defined the mean squared error as the loss function there. So, why is x transpose x mostly positive definite? So, you can follow the same procedure what we did above. You can compute z transpose hz, and in this case the Hessian was 2 times x transpose x. I am going to drop the factor of 2 because it is not going to change the analysis, and just use x transpose x instead. So, this is what we get, and you can rewrite this z transpose x transpose times xz. So, that is basically xz whole transpose times xz, which is essentially the norm of xz squared, and this obviously will be greater than or equal to 0, right. So, if this value is greater than or equal to 0, then it is called a positive semi definite Hessian or matrix, and in this case the matrix is the Hessian matrix, and this happens if the eigenvalues are positive or 0, right, that is they are non-negative. So, I hope you understand the difference between a positive definite matrix, where definitely z transpose h z will be greater than 0 and the eigenvalues are all greater than 0, or a positive semi definite matrix where z transpose h z is greater than or equal to 0, and that can happen if some eigenvalues are positive, some are 0, but they have to be non-negative for this to be necessarily true, right. So, therefore, the Hessian in the minimization of the mean squared error of a linear regression problem is positive semi definite, and thus most likely we are at a local minimum, right, when we did the minimization and we found the parameters equal to x transpose x inverse x transpose y. So, I hope this clarifies the question you may have had in one of the previous lectures. So, let us go ahead and write down the complete set of conditions, right, in terms of what we encountered for the Hessian. So, I will start with, right, what happens to the points in terms of them being local minima, maxima or a saddle point. So, there are 3 cases. The first is that if all the eigenvalues of the Hessian are positive, then the Hessian, which is the matrix of second order derivatives that I had written down in the previous lecture, this Hessian is positive definite, and the point at which you found the Hessian, right, and the considered point is a local minimum. The second case is if all the eigenvalues of H are negative, the Hessian is negative definitive. So, you take any vector, then Z transpose HZ will be less than 0, strictly less than 0, and the considered point is a local maximum. And finally, we have the third case, if some eigenvalues are positive and some are negative, the Hessian is indefinite. So, you cannot comment on the sign of Z transpose HZ. It can be positive, negative, 0, right. So, the point is neither a local minimum nor a local maximum. It is instead what is called a saddle point. Okay. So, this completes our discussion of the concept of the Hessian and why it is so important. Now, what we will do in the next lecture is we will discuss how the learning rate is going to impact the training process. If you remember the gradient descent process, we do have to define a learning rate, and if the learning rate is too high or too low, that is going to definitely impact the training of the ML model. So, our endeavor will be to find the optimal value of the learning rate, and this is something that we can do only by proper testing while the training is happening. So, I hope you learned something in this lecture, and I was able to answer any queries you may have had as to why, when we considered the linear regression problem and we determined the second order derivative matrix to be X transpose X, we said that most likely it's the optimal set of parameters corresponds to a local minimum. Thank you for joining today, and I look forward to seeing you next time.